Okay, so hello and welcome back. So in the previous videos we talked about a couple of things. We came all the way up to this point where we talked about accuracy, precision, and uncertainty. And now what's important here is that basically we said that over here. Let me start from this part in the text, which is accuracy, precision, and uncertainty. The degree of accuracy and precision. So accuracy means how accurate you are, meaning how close you are to the main target or to the true value of the measurement, and that is your accuracy. And precision means that your measurements are all very close together, but probably not very close to the true value of the measurement or not. That's not important. The important thing is that if the measurements are all very close to one another, meaning that you get not of course the exact same values, that's almost never possible, but if you get some values very close to one another, that means that you have been precise. But then if all of those values are also close to the true value of the measurement, then you have been also accurate, right? So what we have here is that uncertainty is the degree of accuracy and precision of a measuring system are related to the uncertainty in the measurements. So what that means is that basically the more that your values are uncertain, and basically one problem that I have here with this text is that I don't really understand what they mean by the term uncertainty or uncertain, because they haven't defined it. They have talked about so the measurement in the paper example are both accurate and precise, but in some cases measurements are accurate but not precise, or they are precise but not accurate. Let us consider an example of a GPS system that is attempting to locate the position of a restaurant in a city. Think of the restaurant location as existing at the center of the bull's-eye target, and think of each GPS attempt to locate the restaurant as a black dot. Now in figure 1.24, which is this figure over here, you can see that the GPS measurements are spread out far apart from each other, but they are all relatively close to the actual location of the restaurant at the center of the target. This indicates a low precision, high accuracy measuring system. However, in figure 1.25, the GPS measurements are concentrated quite closely to one another, but they are far away from the target location. This indicates a high precision, low accuracy measurement system, as you can see here. So the location of the restaurant is right in the bull's eye, and this basically means that what this measurement system is telling us is that all of these measurements are kind of very close to the actual location of the restaurant, which is right in the center of this circle, right? And so this means that this measurement or basically all of these measurements are, at least relative to these measurements, are much more accurate. But then over here, as you can see, the measurements are at least relative to these measurements are not at all close to the actual value of the measurement or the location of the restaurant. And what that means is that this measurement system denotes a system that has low accuracy but of course high precision. As you can see, all of these measurements are close to one another, right? So a GPS system attempts to locate a restaurant at the center of the bull's eye. The black dots represent each attempt to pinpoint the location of the restaurant. The dots are spread out quite far apart from one another, indicating low precision, but they are each rather close to the actual location of the restaurant, indicating high accuracy. So what we have here is that the dots are spread out quite far apart from one another, indicating low precision, but they are each rather close to the actual location of the restaurant, indicating high accuracy, right? And in this picture, in this figure 1.25, the dots are concentrated rather closely to one another, indicating high precision, but they are rather far away from the actual location of the restaurant, indicating low accuracy. Okay. Now, now we have something here called accuracy, precision, and uncertainty. So the degree of accuracy and precision of the measuring system are related to the uncertainty in the measurements. Now, I don't understand this statement because I don't understand what they mean by uncertainty, because it could mean anything as long as you haven't defined it. And so uncertainty is a quantitative measure of how much your measured values deviate from a standard or expected value. So they have defined uncertainty as a quantitative measure of how much your measured values deviate from a standard or expected value. Okay? If your measurements are not very accurate or precise, then the uncertainty of your values will be very high. Okay. In more general terms, uncertainty can be thought of as a disclaimer for your measured values. For example, if someone asks you to provide the mileage on your car, you might say that it is 45,000 miles, plus or minus 500 miles, for example. The plus or minus amount is the uncertainty in your value. That is, you're indicating that the actual mileage of your car might be as low as 44,500 miles or as high as 45,500 miles, or anywhere in between. All measurements contain some amount of uncertainty. In our example of measuring the length of the paper, we might say that the length of the paper is 11 inch plus or minus 0.2 inch. And the uncertainty in a measurement. Now, of course, if you don't understand these parts, it's necessary that we actually ignore a couple of things here, and then in the exercises we will take care of them, hopefully. I have been looking for a good introductory basically book on or course on physics, and so far this seems to be the best one, because any physics text that you pick up, you will run into problems, meaning that it seems that there is no physics textbook available in the world which is like a completely logical system. It's just that I've never actually seen such a thing, and I have read most of the physics books available most of the famous, for example, well, I don't want to mention any names, But even if you go for the very famous physics texts, they all of a sudden they throw a couple of numbers at you and you don't know where those numbers come from. So I don't know, it's just that way. So if you don't understand something, you'll have to probably ignore it and hope that you will understand it later, or probably just simply ignore it, because there's no other way to deal with this sort of thing. And the uncertainty in a measurement A, so suppose that you have a measurement A, is often denoted as delta A. So the measurement result would be recorded as A plus or minus delta A, meaning that the measurement itself is A, right? And the uncertainty in your measurement is expressed as delta A. So the result of the measurement would be recorded as A plus or minus delta A. What that means is that if you have some measurement, let's call it A, the uncertainty in the measurement A is denoted as delta A, and so the measurement result would be recorded as, so the measurement result would be recorded as A plus or minus delta A, right? A plus or minus delta A. Now, basically the factors contributing to uncertainty in a measurement, include, so the factors contributing to uncertainty in a measurement include limitations of the measuring device. Of course, the more limited your device is, the more uncertain your measurements are going to be. And the skill of the person making the measurement, meaning that the less skillful the operator of the apparatus is, the more basically uncertain your measurements are going to be. Irregularities in the object being measured. If you're measuring something which is hard to measure, meaning that there is irregularities in it of any sort of or kind, then those irregularities are going to show themselves as uncertainty in your measurement, of course, because you have to basically let others know that, for example, this was some type of measurement where you had no control over certain aspects of the measurement, and therefore, because of those irregularities, you are, for example, introducing 5%, 10% uncertainty into the measurement so that the numbers are trustable. And any other factor that affects the outcome which is highly dependent on the situation. So, for example, now there is different types of examples that you can basically give here. But in our example, such factors contributing to the uncertainty could be the following. For example, the smallest division on the ruler is 0.1 inch. The person, meaning that you cannot go any higher in resolution. You cannot go any higher than 0.1 inch. Or the person using the ruler has bad eyesight, right? Or one side of the paper is slightly longer than the other, meaning that creates problems in your measurements. And at any rate, the uncertainty in a measurement must be based on a careful consideration of all the factors that might contribute and their possible effects, right? And here we talked about the uncertainty in a measurement using a thermometer, and we said that basically a thermometer that is used for measuring human body temperature, if it has, for example, 3 degrees Celsius uncertainty, then it's as good as useless. Meaning that, for example, when you have a reading 35 degrees not centigrade but Celsius on your thermometer, it could be 33 or 34. It could be any number between 34 and 40 degrees Celsius, and you simply don't know, and you have to make room for all of that uncertainty that comes in with that thermometer. Meaning that you just simply don't know with certainty what the number is. The number could be, what you know is that the number could be anything between 34 degrees Celsius and 40 degrees Celsius. That you could know, that you would know, but then more than that you just don't know. Now, there is one more thing here, which is called, there is something called the percent uncertainty. And you see basically the measurement that you make, we denoted that by A, capital A. The uncertainty in that measurement we denoted by delta A, right? So if you take the ratio of those two numbers, the ratio of those two numbers is going to give you a measure of basically basically it's going to give you a ratio of the uncertainty in the measurement to the measurement. Meaning that, for example, in this particular case, you would have, for example, the uncertainty here, if you take the uncertainty as 3 degrees Celsius, this would be 3 degrees Celsius to 37 degrees Celsius. So that would be 3 to 37. And that gives you some number like, for example, I don't know, 5%, 10%. And you multiply that by for example, by 100%, and that gives you percent uncertainty, meaning that here if you told me that the uncertainty in this measurement is, if you told me that we have made some measurement, you don't tell me about the measurement, or you don't tell me anything about the situation, or you don't tell me anything about the reading. For example, in the exact same thermometer situation, you don't tell me anything about the situation. You just tell me that the uncertainty in that measurement was, you just tell me that you measured some basically temperature, right? And then you tell me that the uncertainty in that measurement was 3 degrees Celsius. So with this information that you have given me, I cannot do anything because I don't know 3 degrees Celsius relative to what, right? Now, this is giving you the uncertainty relative to the measurement. And now I have some context in order to understand what that basically uncertainty means in that particular context, right? And then you're basically expressing that number in percentage, meaning that you're saying that this number, whatever that is for example 2% of your reading, or it's 3% of your reading, it's 5% of your reading. And so then I can make arrangements for myself. So I know that, for example, this number has the uncertainty in this measurement has been 5% of the reading, and then I can do whatever I want to do with that information. I can actually do something with it, right? Now, there is a question over here that makes no sense as far as I know. I mean, at least the last time that I looked at this, that I looked at the question, it didn't make any sense. Meaning that it says that a grocery store sells 5-pound bags of apples. So these bags, that when you say 5-pound bags of apples, that means that on the bag it says that the weight of the apple is supposed to be 5 pounds, and there is no uncertainty. Apparently, there is no uncertainty in. No, actually, there is uncertainty there. You see, I think this uncertainty plus or minus 0.4 pounds is might be actually the uncertainty that you would get on the bag, meaning that it tells you that on the bag it tells you 5 plus or minus 0.4 pounds or something like that, probably. It's I mean that way it makes sense, because the last time I tried to make sense of this number based on these numbers, and I didn't get anywhere actually with that whole with that whole line of thinking, basically. So this grocery store sells 5-pound bags of apples. You purchase 4 bags over the course of a month and weigh the apples each time. You obtain the following measurements. So suppose that you measure those bags that those 4 bags that you buy over the course of a month, and on week 1, week 2, week 3, and week 4 you get 4.8 pound, 5.3 pound, 4.9 pound, and 5.4 pound. Okay. Now you determine that the weight of the 5-pound bag has an uncertainty of plus or minus 0.4 pound. What is the percent uncertainty of the bag's weight? So first observe that the expected value of the bag's weight, A, is 5 pounds. The expected value of the bag's weight is A is 5 pounds. So they have taken A, well, not as the measurement, but as the expected value, which makes no sense again, but let's go with the reasoning. Let's see where that takes us. So you can observe that the expected value of the bag's weight, A, is 5 pounds. The uncertainty in this value, delta A, is 0.4 pound. We can use the following equation to determine the percent uncertainty of the weight. So then you have delta A by 8 times 100%, that gives you 100% uncertainty, and 0.4 times divided by 5 times 100%, it gives you 8%. Now, I don't know now why did they give us these numbers. What am I supposed to do with these numbers? Because if A is the expected value of the bag's weight, and delta A is the uncertainty in your measurement, then 0.4 by 5 times 100% is supposed to be 8%. So what that means is that, as a discussion, they've said that we can conclude that the weight of the apple bag is 5 plus or minus 8%. Well, this makes sense. Consider how this percent uncertainty would change if the bag of apples were half as heavy, but the uncertainty in the weight remained the same. Yeah, because if basically if the bags were half as heavy, then of course you would be dividing, for example, 0.4 by 2.5, you would get about 16%, I suppose. 16%, right? Right. So, meaning that if I divide, meaning that suppose that the bags are, meaning that the expected value of the bag is 2.5 lb, is 0.5 pound or lb, and the uncertainty or delta A is equal to the same thing, 0.4 lb, right? So then in order to, this is delta A. Now in order to calculate percent uncertainty, I would divide delta A by A times 100%, and that would give me basically 0.4 by 2.5, and LB and LB would cancel out, times 100%, and that would give me something like, for example, 0.4 by 2.5. 0.4 divided by 2.5. That's exactly 16%. And here you would get a 16%. This is percent uncertainty, which means that you could write this as, basically you could write the weight of the mass of these bags as 2.5 plus or minus 16% lb, or you can write it as 2.5 lb plus or minus 16%, which is the same thing as that you can write as, for example, what is 16% of 2.5? 2.5 times 16% is equal to 2/5 or 0.4. Right, so we already had it. We already had the number over here. So that means that the actual value of the mass of the bag. So if I take the actual mass of the bag in this case, if I take it as, for example, B, for example, anything B, for example, then you can say that B is some number lying between basically 2.5 minus 0.4, 2.5 minus 0.4, and 2.5 plus 0.4, and of course the units over here are lb, right, or basically pound. So that's what that means. But of course there are many basically questions at the end of this chapter, and we will hopefully know more about these over there, so we don't need to worry about these things. And now the uncertainties in calculations. There is an uncertainty in anything calculated from measured quantities. There is an uncertainty in anything calculated from measured quantities. And of course, you know that, and the reason for that is that these measured quantities have of course uncertainty. When the uncertainty basically comes in through measurement, then that measured value, the uncertainty that is contained in the measured value, is basically then goes into your calculation, of course. Now, for example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties, right? So this is a good example. The area of a floor, the area is basically the product of two lengths, a length and a width, for example. A length and a width, both of which they have uncertainty there is uncertainty in them when you measure them, right? And for the same reason, then these two uncertainties, when you multiply them together, when you multiply these two values together, these two uncertainties in some specific ways add up together to give you an uncertainty in the area that you're calculating, right? And basically, how big is the uncertainty in something you calculate by multiplication or division? This is important. And of course, if you want to know how this happens, we can calculate that, but it's a lot of trouble, so I prefer not to do that. But long story short, how big is the uncertainty in something you calculate by multiplication or division? If the measurements going into the calculation have a small uncertainties, a few percent or less, then the method of adding percents can be used for multiplication or division. So if basically the measurements going into the calculation have small uncertainties, about a few percent or less, then the method of adding percent can be used for multiplication or division. This method says that the percent uncertainty in a quantity calculated by multiplication or division is the sum of the percent uncertainties in the items used to make the calculation, right? So this method says that the percent uncertainty in a quantity calculated by multiplication or division is the sum of the percent uncertainties in the items used to make the calculation, right? Okay, so basically what we said here was that basically there is a method of adding percents, and that is if the measurement going into the calculation have small uncertainties, a few percent or less, then the method of adding percents can be used for multiplication and or division. And we will see in the examples what that means. Now, this method says that the percent uncertainty in a quantity calculated by multiplication or division is the sum of the percent uncertainties in the items used to make that calculation. Meaning that, for example, suppose that for example you measure some length, you want to calculate the area of some area, for example. Suppose that this area, this length is, for example, 4 meters, and this length is 3 meters. There is, for example, 3% uncertainty. There is 3% uncertainty in this measurement. There is 2.5% uncertainty in this measurement, right? Now, the way that so basically this length, I can write it as 3. I can write this length as 3 meters plus or minus 2.5%. This length I can write it as 4 meters plus or minus 3%. And when I multiply these two numbers together, I will get basically 3 times 4 is equal to 12. 3 times 4 is equal to 12. And let's say that this is basically 4. Let me write it this way. To account for the number of significant figures, I'm going to say that this is 4.0 meters. This is 3.0 meters, right? So this measurement will be expressed as 3.0 meters plus or minus 2.5%. That is this measurement. This measurement is going to be expressed as 4.0 meter plus or minus 3%, right? Now, when I multiply these two numbers together, I will get basically 3 times 4 is equal to 12. 12 and 12 meters plus or minus, and then here you have 2.5% uncertainty. Here you have 3% uncertainty. 2.5 plus 3 is equal to 5.5% uncertainty in your measurement here. 5.5% uncertainty here is actually that is square meter plus or minus 5.5% uncertainty here. And that is the area. So basically what this method is saying is that if the measurements going into the calculation, if the measurements going into the calculation have small uncertainties, meaning that a few percent or less, then the method of adding percents can be used. Then the method of adding percents can be used for multiplication or division. And remember that this is only when you are multiplying some two values or dividing some two values. So for multiplication and division. This method says that, this method says that the percent uncertainty in a quantity, that the percent uncertainty in a quantity calculated by multiplication or division, multiplication or division is the sum of the percent uncertainties, uncertainties in the items used to make the calculation. use to make the calculation. Right, so that is basically the method of adding percents is. So as an example, we can say that if a floor has a length of 4.00 meter, so suppose that a floor, so the length, let's say that this is a floor and it has a length of 4.00 meters and a width of 3.00 meters. 3.00 meters. With uncertainties 2% and 1% respectively. 2% uncertainty and 1% uncertainty respectively. Then the area of the floor is 12, so 3 times 4 is equal to 12. Then the area is going to be equal to 4 times 3, which is equal to 12.0, and you can see that I have 1, 2, 3 significant figures here. We will know more about the number of significant figures shortly, but for now I'm just going to tell you that this number has 3 significant figures. 4.00, this has 3 significant figures. This number also has 3 significant figures. Multiply them together, you'll get 3 significant figures. So I'll write this as 12.0 square meters and has an uncertainty of 3% with 3% uncertainty, meaning that 2% plus 1%. Expressed as an area, this is, as if you want to express this as an area, this is so 3% of 12 is basically 12 times 3% is the same thing as divide by 2, you will get, divide by 2 you'll get 6, divide by 2 you'll get 50, divide by 2 you will get 3, divide by 2 you'll get 25. That's 9 by 25. 9 by 25, and what is 9 by 25? 9 divided by 25 is 0.36. That is the same thing as 0.36. So now this uncertainty here, 3%, as you can see, 3% of 12 square meters is going to be equal to 0.36 square meters. And since we had basically and you can see that basically the uncertainty that we had in this number was 1%. The uncertainty that we had in this number was 2%, meaning that 2% has basically one significant figure, right? And also 1% has basically one significant figure. Now when you add these two numbers together, you will get 3%, and basically now and then what happens is that you take your 3%. You need to be careful about these calculations, otherwise your numbers will be unreliable. So now to express this as an area, I have to multiply this 3% by 12 square meters, right? So I write 12.0 square meters, 12.0 square meters times 3%, right? Times 3%. Now, as you can see, this number has 3 significant figures. Has 3 significant figures. This number over here has only one significant figure. As you can see, that is a 3%, and the 3 has basically just one significant figure. So this number, you can take it as one significant figure. Now, when you're multiplying numbers, it doesn't have anything to do with this situation, but when you're multiplying numbers, you multiply some number with 3 significant figures with the number with one significant figure. You have to take the number of significant figures of the number which has the least number of significant figures. And in this case, this number has only one significant figure. You take that number as the number of significant figures for this calculation. This calculation gives you normally 0.36. So this calculation normally gives you 0.36. Now 0.36 has 2 significant figures. But since I need only one significant figure here, I have to round this to one significant figure, meaning that I have to round to this first digit here, which this 3 becomes a 4, and you have to express this as 0.4. And therefore this becomes 0.4 square meters. And so we round to 0.4 square meters since the area of the floor is given to a tenth of a square meter. You can think about it that way, or you can think about it this way as well, meaning that the area of the floor, as you can see here, it has 3 significant figures, but this number has been given to a tenth of a 1/10 of a square meter, right? So since this number has been given to a tenth of a square meter, this number has to be given to a tenth of a square meter as well. Otherwise, it doesn't make any sense. For example, suppose that you say, for example, I don't know, 10 meters plus or minus, 10 meters plus or minus, for example, plus or minus, for example, I don't know, 10 meters, for example, plus or minus 1.0005 meters, right? So you can see that the resolution of this number the resolution of this number is to 1 meter, right? The resolution of this number is 1 meter, meaning that the smallest digit that you have over here is the ones place value. This is over here is the ones place value. So you have the ones place value here. And what that means is that basically I know this length. I mean, the highest resolution that I can get based on this number is either 8 meter or 9 meter or 10 meter. But I have no resolution like, for example, 8.5 meter that I cannot get based on this number, right? And so it doesn't make any sense to basically to say 10 meter plus or minus 1.0005 meters. It just doesn't make any sense, because the resolution of this number is to basically to the ones place value. and the resolution of this number is to the 1/10,000th place value, which is, they don't just simply don't go together, which means that then this number, what you need to do with that is that since this number has been expressed as a given to a 1/10th of a square meter, then you have to express this number also to 1/10th of a square meter, and then that is basically, so then you can say basically the area of the floor, you can say that the area of the floor is basically equal to basically 12.0 square meter plus or minus, for example, 0.4 plus or minus 0.4, which means that the area of the floor, if I take it as, for example, A, then A is some value between 12.0 minus 0.4 square meter and 12.0 plus 0.4 square meter, right? So that is basically what this means, right? So you need to work with these numbers in such a way that it makes logical sense and practical sense. In mathematics, you can do almost anything with numbers. That's not the problem. But then when it comes to physics, physics has its own rules and regulations. And most of the time what happens in physics is that sometimes when mathematics, of course, comes, I mean, the basic language of physics is mathematics, of course. But then when it comes to physics, most physicists basically are of the opinion that basically the mathematics that physicists use is not right, it is wrong. Which is, of course, I mean, they're not wrong, of course. For example, in mathematics, there are certain rules and regulations about integration and integrals and basically the whole calculus and functions and everything that that go together. In mathematics, you cannot do certain things on certain functions, but then all of a sudden, what happens is that, for example, you take a function in physics and then do certain things on it using calculus or some other tool that you wouldn't normally do in mathematics. In mathematics, that wouldn't be there wouldn't be a basically an operation that would be allowed or a valid operation. But then in physics, sometimes you do that because physics is actually using mathematics as a tool in order to talk about natural situations, and these natural situations, none of them is basically an ideal situation. Every situation has all kinds of uncertainties, and you have to take care of all of the different aspects of natural phenomena and so on and so forth, and therefore mathematics becomes a little bit weird in physics. Okay, sometimes, of course, not all the time. Now, the next thing that we have here is a part that is about check your understanding, and it says that the high school track coach has just purchased a new stopwatch. The stopwatch manual states that the stopwatch has an uncertainty of plus or minus 0.05 seconds. Runners on the track coach's team regularly clock 100-meter sprints of 11.49 seconds to 15.01 seconds. I think what that means is that runners on the track coaches team regularly clock 100 meter sprints of 11.49 to 15.01 seconds. What that means is that probably I'm not familiar with this sort of thing. Specifically, I'm not familiar with any sort of sports of any kind, most of the sports. I would say none of them, but well, I would say that this means that they run a distance of 100 meters in some time interval, usually between 11.49 seconds to 15.01 seconds. And so this clock is this timer or stopwatch is not precise. It doesn't have enough resolution to measure this thing over here, right? Now, because there is already an uncertainty. There is an uncertainty in this digit here. Plus or minus 0.05 seconds. Okay, meaning that the reading on the stopwatch, it has an uncertainty. Okay, so let's read through the problem. At the school's last track meeting, the first place sprinter came in at 12.04 seconds, and the second place sprinter came in at 12.07 seconds. Will the coach's new stopwatch be helpful in timing the sprint team? Why or why not? And the solution is no, the uncertainty in the stopwatch is too great to effectively differentiate between the sprint times. So let's think through this problem, because this is a problem that is, first of all, interesting, related to numbers, and of course important in terms of physics. So let's see how we can understand this problem. Okay, so first of all, this problem, basically it says that the high school track coach has just purchased a new stopwatch. The stopwatch manual states that the stopwatch has an uncertainty of plus or minus 0.05 seconds. And runners on the track coach's team regularly clock 100 meter sprints of 11.49 seconds to 15.01 seconds. Now these two numbers are, I suppose, useless, because it's just not, I mean, you don't actually need these two numbers in order to do anything with them. This is just something that usually happens on his team. At the school's last track meet, the first place sprinter came in at 12.04 seconds, and the second place sprinter came in at 12.07. So you can see that the difference between the time, basically between the time that the first sprinter came in and the time that the second sprinter came in, is basically 0.03 seconds, right? That is basically in the hundredth of a second, and in the hundredth of a second. And will the coach's new stopwatch will be helpful in timing the sprinter's team? So here you can see that the answer, if I assume that, for example, the stopwatch basically reports time to 100th of a second, meaning that, for example, it gives you time, for example, I don't know, a digit here, a digit here, and a digit here, and a digit here, and this is 100th, this is 1/10th, and this is 1's digit, and this is 10's digit, and probably another digit here, which is probably, I don't know, the hundredths place value, right? So if the stopwatch is reporting the time in this format, for example, then you have plus or minus 0.05 seconds uncertainty there. In whatever it shows you, there is well, I guess within the range of what it can report, there is, because otherwise, I mean, usually this number is relative to some other number, but now we can also assume that, for example, relative to the range of the time that it can report or it will report, on average there is there is plus or minus 0.5 second uncertainty there. These are all assumptions that I'm making. Otherwise, there is not much information on this situation, according to the problem. Which means that basically whatever time you get from the stopwatch, you have to assume that basically this number could be basically any number. For example, suppose that you get 212.25, for example, seconds. That is the reading that you get from your stopwatch. Now this number has to be reported as 212.25 plus or minus 0.05 seconds. 0.05 seconds. Which means that this number could be anywhere between basically, if I call this, for example, if I call this A, then A could be anywhere between, for example, 212.25 minus, for example, 0.05 seconds and 212.25 plus 0.05 seconds. And that's basically, this number could be anywhere between these two numbers. Now you can see that the first sprinter here, the first sprinter came in at 12.04 seconds. The second sprinter came in at 12.07 seconds, right? Now, the difference between the time that the first sprinter came in and the time that the second sprinter came in is only 0.03 seconds. The difference is equal to 0.03 seconds. Now you need a stopwatch that has an uncertainty at least above 0.03 seconds, so that it can actually show you the 0.03 seconds. And this stopwatch has an uncertainty of 0.05 seconds, which means that it just cannot show you that sort of resolution. Meaning that the whole time interval of 0.03 seconds would be lost within the uncertainty of your stopwatch, right? So that's the best way that I could actually explain this. And but one thing which I need to tell you is that usually when you unless you really work in physics, even physicists I've never actually been a physicist, but I know about engineering. So basically engineering, and when it comes to engineering, of course you have to deal with numbers, and of course all of these dealing with numbers, meaning that all of the rules of significant figures and adding the percent and so on and so forth, right? So that means that all engineers must be every day carrying a calculator around and adding 1 plus 2, 3%, 3% plus or minus this and that, and so on and so forth. In reality, an engineer doesn't really care about all of these things. He does care about all of these things, but in his own way, meaning that, for example, once you do your engineering, for example, in electronics, then what happens is that you get a feel for your numbers. Meaning that you know, for example, what sort of resistors you have at your disposal, what is the range of tolerance of your, for example, transistors, what's going to happen to your capacitors, and so on and so forth. And you intuitively know how to deal with your numbers, meaning that usually you don't really need to be so meticulous about your numbers. But of course, all of these things that we learn here actually do make sense. Once you learn them, then gradually you will get a feel for your numbers, and then you don't have to be so meticulous about these significant figures and digits and so on and so forth. Meaning that, for example, I've been working in the field of electronics for not even very long, like for example 15 years or so, and I wasn't even working with numbers that much. I was working practically with different systems, but even then, if you give me, for example, some circuit about something, I know how to basically I know how to deal with my numbers. I know how, and I do understand the range of the numbers. For example, if you tell me that this is the range of the output voltage of this circuit, such and such circuit, I know that, for example, I should, for example, add, for example, at least 10% of tolerance to that value, and so on and so on. It depends on of course, it all depends on the situation, depends on the circuit that you're working on, and so on and so forth. But you will get a feel for all of these things once you get into some practical field of within physics, basically. Okay, so now what I'm going to do is that in the next video we will talk about precision of measuring tools and significant figures. And so I'll see you in the next video, and thank you.